Hello. Okay, so the purpose of this video is to teach you about parent functions and how they can be transformed. Okay, so let's look at each of these graphs that we have here. Okay, so we have this one. So we have the absolute value. We've dealt with absolute values before. If you were to graph something like this, it's going to have the shape of a V. Okay, we dealt with parabolas recently. So if you were to graph this, it has that shape. As well as cubic functions, if you graph it, they have opposite end behavior. And we have square roots. So we dealt with that recently as well. So that's basically what the graph of a square root would look like. Okay. It would be good practice to commit these graphs to memory because that will help with the next part that I'm going to go over. Okay. But anyway, so let's go ahead and just get out of this. And oops, let's say I were to graph each of these. Okay, so let's say we start with our parent function. So our parent function f of x equals the absolute value of x. Okay, so this is our unshifted absolute value function. Okay, let's say that we were to shift it. Okay, so for example, let's create another function. So g of x equals, let's say I do absolute value of x here, but then let's say I manipulate the outside of the absolute value. Let's say I were to subtract 4. Okay, as you can see, if I subtract 4 here, basically what's going to happen is this shifts 4 units down. Okay, if I put a plus here, it's going to be a vertical shift up. That would be 4 units up. But let's say we go 4 units down. Okay, if I were to manipulate the x's now, let's say I like add 3 or something. So as you saw, what this means is that this graph is shifted 3 units to the left. Similarly, if I went the other way, so this would be, it looks something like that. But anyway, so let's just leave it what we had here. So if I consider what we have here, so if we look at each of the vertexes of these graphs, so our parent function starts at 0, 0. But then if we look at our transformed function, what we have is that this absolute value graph is shifted 3 units to the left and 4 units down. Okay, so that's generally how that works. Okay, similarly, if I were to change this, let's say I change up some of these here. Okay, so let's say I change it to a plus 5. So like I showed you earlier, right? So if I do something like this, this is shifted 5 units up, vertical shift 5 units up. And then if I were to go ahead, let's say I subtract 2. Okay, so if I subtract 2 here, what we see is if I compare each of these vertices, okay, so if we compare the blue graph compared to the red graph, basically what's happening is the blue graph is shifted 2 units to the right and 5 units up. Okay, so that's generally how the absolute value graph is shifted. Okay, let's look at another example. Okay, so let's say I change this up. So let's say f of x is x squared. Okay, and then let's go ahead. I change this up. So this is x squared, like minus 3 or something. Okay, so just by looking at this, so you see the outside here, this indicates that we haven't changed the x's anyway. So this says that we're going to shift this parent function, our parent function f of x equals x squared, we're going to shift it 3 units down. And that's exactly what we have here. Okay, so that shifts 3 units down. Let's say I change up the x's now. Okay, so let's say I change up the x's in here. So let's say I put like a x minus 4 in here. Okay, so if I manipulate the x's, let's say if I use a subtraction here, it's actually, if you saw the pattern from the other problem that I showed you, this is going to shift 4 units to the right. So let's see, yeah. So if we compare each of the vertices, so what we have is our parent function starts at 0, 0 here. Okay, if we look at our transformed function, basically what we have is this goes 4 units to the right and this is 3 units down. Okay, based on what we have there. Okay, similarly, let's say I change it up. Okay, Let's say I change this up. I put x plus 1 and x plus 4. Okay? The 4 on the outside indicates a vertical shift. So that's going to go up. Let me just, let's see if I can take that out. Yeah. There we go. Yeah. So as you can see here, this says that we're shifting 4 units up. Okay? But let's say I put it back in. If I put this back in, this indicates the plus is going to shift to the left. Okay? And that's exactly what we have here. So if we compare each of these vertices, what we have here, basically the parent function is shifted 1 unit to the left and 4 units up. Okay, let's go ahead and look at another type of example. So let's consider the cubic function. Okay, x cubed. Okay, so x cubed looks something like this. And then let's say I manipulate this here. So let's say I put a cube here, and I put a minus, and then I put like a -2 here. Okay, so if I have you kind of think about what's happening, okay, so the number on the outside here is going to be your vertical shift, whether it goes up or down. The minus sign is going to shift 2 units down. Okay, and then this here, the -1 indicates when we're manipulating the x's, that's going to shift 1 unit to the right. So let's see. Yep. So that's exactly what we have here. So if we consider our parent function, which is going to be x cubed, basically this parent function is shifted 1 unit to the right and 2 units down based on what we see there. Yeah, so something right around there. Yep. Okay. Let's go ahead and consider another example. So let's say I change this up. Okay, so let's say I change it up, make it x plus 4, and this is x plus 5. Okay, so just by kind of looking at this, well, I see the number on the outside, this is our vertical shift, so it's going to go 5 units up. And then this here, this we have a plus 4, so that's going to indicate a horizontal shift to the left. Okay, so let's go ahead and see if that's, yep, I think that looks like what we have. Okay, so this is where we start at. Our parent function is x cubed at 0, 0. If I were to compare it right here, so let's see, hopefully I can, there we go. Okay, so as you can see what we have here, basically this graph is shifted 4 units to the left and 5 units up. Okay, so that's how that one works. Let's go ahead and look at another type of example. So let's look at the square root function. Okay, so square root, in order to type in square root, you can put sqrt, and I'm just going to put square root of x. Okay, let's say for this one, so I do the same thing, sqrt, and I put x plus 2 minus 3. Okay, if you kind of see a pattern what I'm trying to get at, okay, so this means that this on the outside here, this represents our vertical shift. So it's going to represent 3 units down. And then this, if we manipulate the x's on the inside, so then the plus is going to indicate a shift to the left. So let's see. Yep. So that's exactly what we have here. Can I click on this? Oh, cool. Yes. Okay, so just to kind of show you what this does, right? So basically, we start at 0, 0. 0, 0 is our parent function. This represents our parent function, which is the square root of x. Okay, when we consider our parent, our transform function, basically what we have is you're shifting it 2 units to the left and 3 units down. Okay, let's go ahead and look at one more example. So let's say I change this up now. So instead of x plus square root of x plus 2 minus 3, let's say change it up. I put a minus 4 here and a plus 6. Okay, based on kind of what you saw earlier, basically what's going to happen is this graph is going to shift 6 units up, and it should shift 4 units to the right. So let's see. Yep, and that's exactly what we have here. So this is our parent function. Our parent function is the square root of x. Okay, and then basically it's shifted 4 units to the right and 6 units up. Okay, so let's create a summary. Let's create a summary of what just went over. All right, so in summary, basically what we have here, well, just think of this all as what we did with the transform function, g of x. But basically, if you were to manipulate the x's in such a way that so this plus here is going to represent a shift to the left, the minus sign, if you're manipulating the x's, is going to shift the graph to the right. If you're doing something on the outside, this is going to shift it up, and this shifts down. Okay, so just watch out for some of those things as you go through these problems. Okay, let me know if you have any questions. Okay, bye. Hello. Okay, so in this video, I'm going to talk about reflections across a specific axis. Okay, so let's say we have our function f of x equals absolute value of x. So this is our parent function. Okay, let's say we take this parent function and we put a negative in front. Okay, if we put a negative in front, what we're doing is we're just changing the y values. We're not manipulating x's, we're just changing the y's. So this says if we put a negative in front here, basically, as you can see here, this graph is reflected across the x-axis. Okay, similarly, let's say I change it up. Let's say I put x squared here, x squared, and if I change this to negative x squared, this is something we've dealt with before. I think it was unit 1. But if you put a negative in front, it's going to flip it over the x-axis. Okay, change it to a cube. Okay, so that's what that's going to look like. But then if I put a negative in front here, it's going to, again, just flip it across the x-axis in blue, that you can see there. Okay, and then let's say it changes up. Let's say I put square root of x. Okay, so that's that one. If I take this here, there we go. And let's say I put a negative in front, so negative square root of x. So this is also going to flip across the x-axis. Okay. Now, let's say I change it up just a little bit. Okay, so for example, let's say I make it just a little bit tougher. You know, like with the functions that I showed you previously, like let's say something like absolute value of x plus 3 minus 4, right? So if I took this here, if I took this here, and then I put a negative in front, so as you can see, that negative here, if I just toggle it, as you can see, it flipped it across that specific axis right there. And you can do that with a whole bunch of these, honestly. So let's say I just put this here. Okay, so like, whoa. Okay, so x minus 4 squared minus 3. So if I put a negative, see if I put the negative in front, it kind of plays around with that, and so forth. So you can play around with a whole bunch of those. Okay, there is a difference though. If I were just to manipulate the x part. So if I were to manipulate the x on the inside here, so as you can see, now this is reflecting across the y-axis instead. Okay, so there's a difference if I do this compared to this. Okay, so that would be an example where you're reflecting across the y-axis. Similarly, let's say change it up. So let's say I put like x plus 3 here minus 4. So if I put the negative in front here, so as you can see, it's reflecting across the y-axis. But then if I do this, it's going to reflect along that particular line. If the function wasn't transformed, it would be reflecting across the x-axis. Okay, and so in general, if I would just kind of show you this, that's basically what I meant. So if you're doing a change on the outside, basically it's negative. This is going to be a reflection across the y-axis. I'm sorry, this is going to be a reflection across the x-axis. Let me put that in a different color. And then if you have the negative in the inside, this would be a reflection across the y-axis. Okay, and that's it for this video. Okay, bye. Hello. Okay, so now I'm going to talk about vertical stretches and compressions. Okay, so let's say the number on the outside here, let's say we put a 3. So we have 3 times the absolute value of x. So as you can see here, what happened to our parent function f of x, or in this case, it was vertically stretched by a factor of 3. Okay, so that would be multiplied by 3 on the outside. If I change this up, let's say I make it something between 0 and 1. So let's say like 1/3 or something. This represents a vertical compression instead. Okay, so that's kind of how that would work. Let's say I change this up. So let's say I put let's say I put x squared here, and I change this to 4x squared. Okay, so same idea. If I were to show you this, so if this number here is greater than 1, so it's going to vertically stretch yeah, by a factor of 4. But if I change it to a number that's between 0 and 1, so as you can see, the green graph here is being vertically compressed. Okay, so that would be 1/4 x squared. So there's a difference between this and this. Okay, let's go ahead and look at, I have one more example here. Okay, so we have the cube. So this is what our parent function x cubed looks like. Okay, and then let's say I change it up. Let's say I change this to like a 5x cubed. Okay, so as you can see, this parent function is it's vertically stretched, in this case by a factor of 5. And then if I change this to a number between 0 and 1, then this is going to vertically compress instead. Okay, so the general summary that I have for you guys is here. Okay, so if the number on the outside, in this case here, if this is greater than 1, then you have a vertical stretch. If this number here is between 0 and 1, it's going to do a vertical compression. So think about what we have here, right? We said 1/5. Well, 1/5 is the same thing as like 0.2, right? So they both basically are the same thing. Okay, so if you see a number, if it helps some of you, like it's good to go ahead and just convert that fraction. Let's say I just put like 3/16. So, or like if I change it to like 3/8. These are all examples where it's less than 1. But if it's greater than 1, let's say do 1.5 or 2, 3, 4, 5, or 6. So as you can see, basically it's stretched instead of compressed, like this example here. Okay, and that's basically it for this example. Okay, please let me know if you have any questions on anything. Okay.